This section's all about linear differential equations. We've seen some that were separable and linear. Now we're going to look at just the general linear differential equations. So we're going to solve them using something called an integrating factor, and that will allow us to solve mixing problems where the in and out rates are different. This is the format of our general differential equation. dy dx is equal to some function of x times y plus some function of x times y is equal to some function of x. So there's no y's mixed in with our derivative. That's what makes it linear. If these two functions are just numbers, then this is separable. And we learned to solve that way back in section 9.3, way back last week. So if these are just numbers, then it's c e to the negative kt minus b over k. It's really easy. But let's suppose we don't have something that simple. We have a differential equation that looks more like this. And let me catch up with where we are. There we go. It's an example of a linear equation that's not separable because we have that x sitting there. It keeps it from being separable. So our goal, kind of like our goal back when we learned integration by parts, is to make this look like a product rule, because then we have y primed times x and then the derivative of x times y. So yeah, we're going to make it look like a product rule. Here we go. Here's our product rule. The derivative of x times y is x times the derivative of y plus y times the derivative of x. Well, I have a y primed and I have a y. I'd want an x to be multiplied here by this y primed, and I want to get rid of this 1 over x multiplied by the y. So I just multiply both sides by x. So now x times y primed plus y times x primed is equal to 2x. That's the derivative that I wanted, and I can solve this linear differential equation by throwing integrals on each side. So x times y has to be equal to x squared plus c. So y has to be x squared plus c over x. Well, the magic is that you can come up with the perfect function to multiply both sides by to turn your left-hand side into a product rule. We just have to figure out what that is. Okay, so let's look at our general equation. dy dx is equal to some function p of x, and we're always going to want to get it into this format so we can find our p's and q's, because our p's and q's are important. Our goal is to find this integrating factor, so that I take this integrating factor, multiply both sides by the integrating factor, and I want it to turn into the derivative of I times y, excuse me. So I times y primed is equal to I times y primed, because I'm just distributing over here on the left-hand side. So this is my goal, is to figure out what this I needs to be. If I can figure out what this I needs to be so that this is equal to that, well, it also has to be equal to I times q, because that's from the original equation. So I'm going to have to multiply both sides. So I times q is going to have to be equal to this integral, to this derivative, the derivative of I times y. And the derivative of I times y needs to be equal to I times y primed plus I times p times y. because that's the two sides of my equation. Well, if I can figure this out, then it'll be really easy, because the integral of this derivative would just be equal to the integral of I times Q dx. So I'll end up with y is equal to the integral of IQ over the integrating factor. Let's see if we can figure out what the heck this magical integrating factor needs to be. So I'm going to take this I of x times y primed plus I times p, and then I'm just writing down this derivative. So I times y primed plus I prime times y. Well, I have I prime times y on both sides here. So this means I of x times p of x times y has to be equal to I primed of x times y. Everybody's got a y. So I of x times p of x has to be equal to I primed of x. Well, that's something that I can throw integrals at. The integral of p of x times I primed of x over I bring this I over here with this I primed. I can divide it into p's and i's. Well, the integral of p will have to be equal to the integral of I primed over I. Oh, that's the natural log of I. So my integrating factor has to be equal to e raised to the integral of px. There's my integrating factor. Hopefully you followed all that. But then I of x is equal to the integral. I of x times y is the integral of I times q. So here is our summary. Y will be equal to the integral of IQ over I, and the integrating factor is e raised to the integral of p of x. Let's look at an example. So, already in standard form, that was my step one that I was referring to here, is to get it into standard form. So, dy dx plus p times y is q. I write down my p's and q's just because it helps me to keep up with what's going on. So my p sits next to my y, my q is on the other side of the equal mark. Then I compute my integrating factor. My integrating factor is e to the integral of p. So p was 3x squared, so e to the x cubed. So now I multiply both sides by e to the x cubed. Now, I'm not using this little formula right now. I'm showing you yet again why it works, just in case you didn't follow it with all of the p's and q's and i's in it, doing it step by step with a real function. So I figured out the special function. I multiply both sides by that special function, the integrating factor. Then you can see I have e to the x cubed dy dx, 3x squared e to the x cubed. Well, that's the derivative of this little function, the integrating factor, times y. That's why this works. And then I have I times q over here on the right-hand side. When I take the integral of this, because this is the derivative of e to the x cubed integrating factor times y, I get integrating factor times y. Then I take this integral. It took some u substituting. I let u be equal to x cubed. Then du was 3x squared dx. I had 6x squared, so that gave me 2 times e to the u du, which is 2 times e to the x cubed, because integral of e to the u is e to the u, and u is x cubed, so plus c. So y is equal to the integral of I times q divided by my integrating factor. Always going to work for you. Integral of IQ over I. So, pretty answer. There's the nice blue box with your summary. And there's the pretty answer. Now we have an initial value problem. So, let's write down our initial value problem. This time, it doesn't start out in perfect general form. We have an x squared sitting next to my y prime. So I divide everybody by x squared to get it into general form so I can write down my p and my q. My integrating factor is e to the integral of p, which is x to the minus 1. I just wrote it as dx over x, which is the natural log. And you notice I just kind of ignore the absolute values there. That's okay because my x is greater than 0 in this case. And usually we just think of kind of absorbing that into our constant. So we don't have to have every integrating factor. We just have to have one that works. So if I just look at the ones where x is positive, I'm going to have one that works. So we're okay. So e to the natural log of x is just x. Step 3. I computed my integrating factor. Step 3 is to do the integral of IQ over I. So IQ over I. Here's I. Q was x to the minus 2. And then I simplify. I end up with dx over x. So natural log of x again. Natural log of x plus a constant over x. I can divide it into two pieces. And step 4 is to determine what my constant is because I had an initial condition, so I need to figure out what my c is. I plug in 1 for x, 2 has to come out as y. Natural log of 1 is 0, so my c has to be equal to 2. And you can see in the pretty solution, I left it as one term. Here I wrote it as 2. They're the same. So here are your practice problems. Try the first one. It's already in the general form, so you can figure out exactly what your p's and q's are. You don't have to do any dividing, and then we'll go over it together. So my p is the function that's sitting there next to y, which is just minus 1. Q is e to the x. So my integrating factor is e to the negative 1 dx, which is e to the negative x. So I multiply IQ over I. Integral of e to the negative x times e to the x, well, it's just the integral of dx again. So I end up with x plus c over e to the negative x. And usually we get rid of the fraction and write it as simply as we possibly can. Try part B. Now remember, you're going to have to divide everything by 2x so you can get it into your standard form. How did that one go? Well, I divided everything by 2x. 2's canceled here. And I ended up with my q of x is just 1 over the square root of x, or x to the minus 1/2 power. P of x was 1/2 of x to the minus 1 power. So 1/2, 1 over x dx. So that gives me 1/2 of the natural log of the absolute value of x. Well, I'm square rooting it, so it's natural log of x to the 1/2 power. Yeah, you have to remember the laws of logarithms so that you can simplify it, because why would you want it to be e to the 1/2 of natural log of x when your integrating factor could just be x to the 1/2 power? Way easier. So now y is equal to the integral of I q over I. Don't think they're all going to turn into just dx. Life's not that easy. But in this case, you end up with the integral of dx again. So x plus c over x to the 1/2 power. So we have x divided by x to the 1/2 is x to the 1/2. And then c times x to the minus 1/2. Okay, try that first initial value problem. Divide everybody by t cubed before you get started and find your p's and q's. So first thing I did, I divided everything by t cubed. Then I ended up with p of t. I have t squared over t cubed, so it's just 3 over t. And then q of t was cosine over t cubed. My integrating factor is e to the integral of 3 over t dt. So that's 3 times the natural log, which is the natural log of t cubed. So my integrating factor, t cubed. Integral of t cubed, cosine of t over t cubed. How convenient. I end up with just the integral of cosine of t, which is sine of t, plus a constant, divided by t cubed. I plug in my pi, and 0 has to come out. So 0 is equal to sine of pi, which happens to be 0, plus c over pi cubed. So c has to be equal to 0. Y is sine of t over t cubed. Look at the next one. Be careful. You're going to have to do some algebra before you start dividing everything. So I distributed that 3x, and then I added it to the other side so that I could figure out my q and my p. My integrating factor is equal to e raised to the 3x over x squared plus 1. So I did a little u substituting. U was x squared plus 1, so du is 2x dx. So I needed to pull that 3 out in front and then multiply by 1/2 to make up for this extra 2 here. So I ended up with 3/2 of the natural log of x squared plus 1. Becomes an exponent. So I just have x squared plus 1 to the 3/2 power. I q over I. I times q, well, I have the 3/2 power, I have the first power, that leaves me with x squared plus 1 to the 1/2 power. I can use the same u and du that I used right here, so once again, I end up with 3/2 sitting out in front, but then that also happens to be my new exponent, and I divide by my new exponent, and they cancel away, plus a constant. And then it still has q in the bottom. So I ended up with x squared plus 1 to the 3/2 over x squared plus 1 to the 3/2, which is just 1. And then c times x squared plus 1 to the minus 3/2. I plugged in 0. 2 had to come out. So 2 had to be equal to 1 plus c. So c had to be equal to 1. Not too bad. Now we can handle that mixture problem. So, a tank initially holds 600 gallons of a brine solution that contains 50 pounds of salt. Now, the difference between this one and where the in and out rates are the same is that the amount of water is going to change. So you're going to need a little function to represent the amount of water. I called it W. Initially, we have 600 gallons of water. Initially, we have 50 pounds of salt. So Y is the amount of salt. That's what we're trying to find, the dy dx. What we're trying to eventually find a function for is the amount of salt. There's my initial value. Now I'm going to start with just the in and out rates of the water. The in rate of the water is 2 gallons per minute. Salt water is being poured into the tank at a rate of 2 gallons per minute. It's drained at a rate of 5 gallons per minute. So it's coming in at 2 gallons, it's going out at 5 gallons. So it's losing water. The amount of water is going to be 600 gallons plus 2 per minute minus 5 per minute, so 600 minus 3t. Now let's find our in and out rates for the salt, just like we did before. The in rate for the salt was 2 gallons per minute times 1 pound per gallon. Gallons cancel with gallons, 2 pounds per minute. The out rate, 5 gallons per minute, just like with the water. Y pounds in 600 minus 3t gallons of water. So before that was just a number because it wasn't changing. Now the amount of water is changing. And then we divide that into, well, we combine that into 1 unit. So dy dt is equal to in minus out, not in standard form. So we add out to each side. So now I have a P and I have a Q. My next step is to get the right sheet of paper and calculate my integrating factor. E raised to the P, which was 5 over 600 minus 3t dt. Well, I had to use substitute again, so I needed a negative 3. So that became the denominator, and then the 5 just pulled out in front, and I have the natural log of what was in the denominator. So the coefficient becomes the exponent. E's and natural logs undo one another. My integrating factor is 600 minus 3t to the negative 5/3. Integral of I, Q, and Q was 2 over I. I have to do some integrating again. I can use my same u and du again. I ended up with adding 1 to the exponent, dividing by the new exponent, gave me negative 2/3 divided by negative 2/3. I needed a negative 1/3. That came from getting my du's there. And then times 2 because Q was still hanging out. So all that stuff canceled. I was left with just 600 minus 3t to the 2/3 plus a constant on top to the negative 2/3. Then I had negative 2/3 plus 5/3 gives me 3/3, which is 1. And C, and this was negative down below the fraction bar, so it becomes positive. Now I have to go back and find my initial condition. I plug 0 in, 600 minus 0, 600 minus 0 has to be equal to 50. So C has to be equal to negative 550 over 600 to the 5/3 power. Yeah, they're going to come out being that complicated looking. But that's okay. We have our function for the amount of salt at any time t. You can do this. You have learned all of the tricks we're going to learn this semester about differential equations.